Okay, so welcome back. I almost ran out of time in the other video, so I had to switch to a new one. So we left off just talking about the idea of a standing wave, which is basically just a wave that looks like it's bouncing up and down. And there's three different ways you can set it up. You can set it up where the ends are stuck together. You can set it up so the standing wave has open ends on both sides. Remember, that was an example was our flute. The example for ends attached was a violin. And then the one where the one end is free and one end is not. Good examples of that would be a clarinet, or another great example of that would be the equivalent of if I was playing the wine glass. I apologize. I have to think through that one. Indeed, that actually is going to be an example. We're going to find out the water is a closed end and the air above the wine glass is an open end. So our next piece, what we're going to talk about, is just some terminology and how we can figure out what notes or what frequencies we can actually produce to create a standing wave. Okay, so with any sort of oscillator, anything that's going to create a physical wave, we're going to find out that there's one frequency in particular that's the lowest frequency you can go. It's the lowest or the slowest you can have this thing bounce up and down, and it can create a standing wave. Okay, now what we refer to that as, that frequency is referred to as the fundamental frequency. And it's basically the lowest on any sort of musical instrument. It's probably going to be the lowest note you can play. And I don't want to get too descriptive because I did not play musical instruments. So there's a lot more to it than I'm probably going to talk about in here. But basically that lowest note is going to be the fundamental frequency. You can't play any other note lower than that. Okay. And the reason is that if I tried to make a wave that actually had a lower frequency than this one, so right now this is actually the fundamental frequency. If I tried to do that, what would happen is that there's no node anywhere in the wave other than at this starting point and this end point. So if I tried to make this even a lower sound, make the frequency even smaller, what would happen is it would just disintegrate because it has to end on a node and it has to start on a node. So you can't go any lower than that. Now, the same thing is true if I look at it, and I have the examples, if I look at it with two open ends. If I try to go a lower sound than that, a lower frequency, what we're going to find out is that that can't work because, once again, this has to end on an antinode and this one has to as well. And if I try to go an even lower frequency, what's going to happen is that it's going to basically turn into gobbledygook because it can't produce a consistent standing wave. All right. So what we're going to find is that the fundamental frequency is going to be the lowest frequency that you can play a musical note on, basically, and a standing wave we produced. We're actually going to refer to this as the first harmonic. And some of you might have heard of the term harmonic. Some of you might not have. That's totally fine. Basically, what we're going to find out is that if something is the first harmonic, that's going to be the lowest sound, the lowest frequency I can play on that object. Okay? Now, what we're going to find out is that we can actually calculate the notes that you can play on something based off of how it's constructed. Okay? And what we're going to find out is that the most important thing, whenever we're producing sound waves, we're producing notes for music, the most important thing is going to be how fast the sound travels and how long the object is that is kind of carrying the wave. Okay? So, for example, if we're talking about a violin, so we go back to two fixed ends, what notes can be produced are going to be based on how long the string is, so how long the string is from here to here, and how fast the wave can travel through the violin string. Okay? Now, depending on what is being used to carry the standing wave can affect how fast the wave can travel. In this case, this is a violin string, so it's how fast the wave can travel through this string. But what will happen is that as I start to kind of change, if I want to play a new note that's a bit higher, I have to go to what we refer to as the next harmonic. And what I have to do is I have to go up a certain amount of frequency so that now it'll still have two nodes, but it'll now look a little bit different. So what will happen is I click this and say next harmonic. And what happens now is it starts to bounce up and down and up and down. And I'm actually playing a higher frequency note, as you can see right here. Even though it's still not a very high number, that's still a higher frequency than it was before. And if I go even higher to the third harmonic, the frequency gets even higher. But so example, let's say the third harmonic's at 0.201 hertz, okay? If I go back to where it says custom waves, okay, we saw there was about 2 hertz was when it had the third harmonic. If I'm something that's not 2 hertz, so let's say it's 1 point something like this, what's going to happen is, even though it looks like it's kind of a standing wave, it's not actually a true standing wave, because you can notice at the end here, it's not ending on a node. And what would happen is that right now in the simulator, it can still do that because it doesn't care. It's a simulator. In reality, on a violin, this end of the string has to be connected. So what would happen is it just wouldn't play that sound. Nothing would happen because it couldn't produce that standing wave. So you have to create waves that fit certain frequencies to get it to create these standing waves. Okay? And it works. It doesn't matter if it's for 2 fixed ends, like this violin. It can be for 2 open ends, like a flute. And what would happen is that as I increase the harmonic, I increase the frequency. Even though this looks kind of weird, what we're starting to see is that I now have more wave in the same space. So the frequency has gotten a little bit higher. And as I keep increasing the harmonic, so this is now, I believe, the third harmonic, the frequency of the note that's being played goes up. Okay. Now, I know I'm talking a lot of shop about all these different standing waves. Why does that matter to any of us? Why it matters is because if you are building a musical instrument or you're playing a musical instrument, you have to figure out what notes it can produce. And to do that, you have to use a very specific formula. So if you are creating a musical instrument that has basically strings, or something like a flute where it's open at both ends, you have to use the following formula to calculate what notes it can produce. So in order to calculate the frequency of a note for something that is the ends are the same, you start by first figuring out the wave speed, so that V. You need to know how long the string or the pipe that's producing the note is. And then you need to know what harmonic you're talking about. Okay, that's what that little n represents. And it's just basically the number of the harmonic. So to figure out the lowest note you could play, you would say the n is 1 for the first harmonic. You'd measure, hopefully, the length of whatever's producing that. So the length of a violin string, the length of the flute you're playing, or whatever instrument you're using. And then hopefully you would use what the speed of sound, the speed of whatever's carrying the wave. So in the flute, it would be the speed of sound in air, because we're going to find out that's just an air column that's vibrating. In a violin, it would be whatever the speed a wave travels in a violin is. Okay, and that can be a very confusing topic at first to kind of figure out between the two. We're going to keep talking about it, I promise. Okay, but once you've calculated the lowest frequency possible, all you do afterwards is you just change the n number for the harmonic. So let's say for some reason I have an instrument and the lowest note it can play is 100 hertz. That's the fundamental frequency. What that means is that now if I want to play notes that are higher than that, according to this formula, if the fundamental frequency is going to be 100 hertz, then the second harmonic, the next one it can play, would be 200 hertz. And then it would be through the third harmonic, 300 hertz. And then 400 hertz, and keep going up into however many harmonics you could fit in there. And there's a lot of weird science that goes on there we're not worried about. Okay? But all that matters is that your musical instrument can only play certain notes because those are the only notes that produce standing waves. All right? Now, if the ends are slightly different, so if, in this case, it would be if one side was open and one side is closed, which would be, once again, like a clarinet, we're going to find out that it actually works slightly differently. So when the ends are the same, whether it's two fixed ends or two open ends, we're going to find out that the fundamental frequency is basically half the full wavelength of whatever sound is being produced. Okay. If the ends are different, though, what actually happens is that this is actually only a quarter of the wavelength of something that can be produced. Okay. Which means that different sounds are actually produced than they would be normally. So right now, this is only a quarter of the wave that would be produced normally. If I go up a harmonic, what we actually find out is that I can't go up to the next one. I can't go up to the second harmonic. I actually have to go up to the next odd harmonic because I have to have it end on an antinode because of the idea that it's closed on one end, open on the other. Okay? And if we look at that, what that means is that the frequency, normally when we did it when it was two fixed ends or two open ends, it would have jumped up, it would have been doubled. But in this case, because it can't follow that rule, it's actually tripled because we skipped the even harmonics. Okay? And if I keep going, this is actually now the fifth harmonic. And so on and so forth. And in all these cases, I'm creating a higher frequency sound. I'm playing a higher note. But it just, once again, governs what notes I can play based off of what standing waves can be created. Okay? And just like we said, just like we had this formula up here, when the ends are different, the only difference is that you can only use odd harmonics. So the end can only be 1, 3, 5, whatever odd number you choose. And the length now, instead of it being 2 times L, 2 times the length of the string of the pipe, it's now going to be 4 times the length, usually of the pipe or the air column that's producing the sound. Okay? So, with that being said, I know I just said a lot of stuff. I want you to try and practice. So if you could, please, ladies and gentlemen, I want you to take about 3 minutes, and I want you to answer this question. So there's 3 different parts to it. I want you first to know, how long do I need to make a violin string that produces a fundamental frequency of middle C? So basically, that's the lowest frequency it can be. And the middle C is 256 hertz. Okay? And the speed of the wave in the string is 450 meters per second. So my one hint is that this is going to be a standing wave where the ends are closed. So you might want to think about what this formula talks about, the one where the frequency when the ends are closed. Take about 3 minutes, please, ladies and gentlemen. And of course, once again, I would pause the video because I don't have 3 minutes. So pause the video and then reset, and we'll talk about what the answers are.